Okay, welcome back. Today we're going to talk about Chapter 3, Polynomial Functions. We're continuing with Section 3.3, Real Zeros of Polynomials. In the last section, we talked a lot about how to divide out a root and obtain a smaller polynomial in factored form. What we're going to focus on today is knowing which numbers to try as candidates for the roots, and that will allow us to factor larger polynomials with some success. Now, first thing I want to mention is that this will not always be possible. Some polynomials may not have roots that we can easily find by hand. Some polynomials may have roots that we cannot find at all. There is a theorem that we're not going to discuss in this class that says that for polynomials of degrees larger than 4, there may not be roots that we can actually find to any degree of precision. But that doesn't mean that we can't get the basics down for these smaller polynomials. The other thing I'll say is that the book goes into a great deal on methods to use graphing calculators to locate these roots. While I do think that graphing calculators are fantastic tools, I think for the most part, if you're using a graphing calculator to locate the roots, you won't be using most of the techniques in this section. You'll just have the graphing calculator report the root for you. So, as a result, if you do have a graphing calculator and you choose to look at these problems with the graphing calculator, I think that's fantastic, but I also want you to be able to do this by hand. Therefore, what we're going to focus on today is skills that you can use when you don't have a calculator. That way, this will be supplemented by when you do have a calculator. You can understand what's going on in the background, even as the calculator does the process. With all that in mind, let's pick up these skills. The first thing we're going to need is the rational root theorem. The rational root theorem is going to allow us to determine which numbers might be good choices of roots. And here's the theorem. If f of x is a polynomial of degree n, all of whose components are integers, so no fractions or decimals as the coefficients of this polynomial. If r is a rational zero or rational root, so in other words, r is a root of the polynomial that has the form of a fraction, then r is a fraction that is either positive or negative p over q, where p is a factor of the constant of the polynomial and q is a factor of the leading coefficient. What do I mean by this? Well, let's take a look at an example. Let's say I said y is equal to 2x squared plus 7x minus 6. This right here is my an. And this is my a0. What we want to focus on is the factors of these. So the possible values for p could be 1 or 2. And the possible values for q, excuse me, I have this backwards. Those were the possible values for q, is for the leading coefficient. For p, the possible values are 1, 2, 3, and 6. I'm ignoring the negatives because a plus or minus is included in the formula, so we won't need to consider the negatives separately. Thus, the only possible rational roots will be of the form of one of these choices of p divided by one of these choices of q. Now, part of the reason that I am mentioning all of this graphing calculator stuff is that not every single function has any rational roots. Maybe all of the roots have square roots in them. And so I won't be able to use this method because there are no rational roots. But sometimes we do specifically care about the roots being rational. And sometimes it does have rational roots. So we still want to be aware of this method and able to use it. The reason that this works has to do with what happens when I FOIL. Let's just make up an example here. 2x minus 1, and then 3x plus 6. If I FOIL this, I will get 6x squared. Let's see, plus 12x minus 3x, so plus 9x minus 6. And so I see that I'm looking here at 1, 2, 3, 6 in both cases as the possible factors of the two pieces. Now let's look at these two, look at the two factors here. For this first factor, the root is 1/2, and for the second, the root is -2. And notice what happened. I took, to solve each of these pieces, I took these and set them equal to 0, and then what I ended up doing basically was dividing the part with the x. I divided by that piece, and I divided that from the part without the x. So in other words, I divided that linear piece by the constant. So what I ended up getting is a fraction, this first one being basically -6/3, which is equal to -2, and the second one being 1/2, where I took one of these pieces and divided by the other. Well, when I FOIL everything out, all of the constants go into the constant term, and all of the non-constants go into the leading term. This shows why all of these factors will show up, and that's a basic idea of why this theorem works. We're not going to do a full proof here. Let's do an example. Using the rational root theorem, determine the possible rational roots. So we'll once again identify the possible p's and q's. The possible q's from here is ±1 and ±2. The p's is ±1 and ±3. Again, we don't need to include these pluses or minuses as long as you remember that positives and negatives are possible. So all of the possible roots could be 1/1, -1/1, 3/1, -3/1. And then 1/2, -1/2, 3/2, -3/2. 8 choices. It seems like a lot of things to try, sure, but keep in mind, number one, this is only 8 possible numbers out of all possible numbers. That's not that many things to plug in. And number two, we don't actually have to try long division by each of these. We can simply plug them in if we would prefer and see if it comes out to 0, because it will only be a root if it comes out to 0. So we can just plug in these choices. Let's see if we can narrow it down further, though. The way we're going to narrow it down further involves the intermediate value theorem. So the idea is this. I'll begin by doing what I just did, using the rational root theorem to list all of the possible rational roots. We'll put the roots on a number line. Just like when solving an inequality, we'll put in some test values. Now, because there may be like 8 choices, I think using all of the test values might not end up being the best bet. So we're not going to use all the test values, just a couple. You're looking to see where the function changes sign from positive to negative or from negative to positive, because somewhere in there will be a root. That will narrow down the choices of what we need to look at. We'll test the points by plugging in until we find one that comes out to 0, and we'll factor those out. We'll continue factoring until we're done. The first couple times will be this process repeated, but eventually we may get it down to a form where we can apply a more traditional factoring technique, potentially factoring by grouping, potentially quadratic formula, something that we already knew. Let's try an example here. I would like to fully factor this piece here, -2x³ plus 19x² minus 49x plus 20. First thing we'll do is we'll list the p's and the q's. So this is going to be 1 or 2. And this is going to be 1, 2, 4, 5, 10, 20. So the possible choices for R is going to be plus or minus 20, plus or minus 10, plus or minus 5, plus or minus 4, plus or minus 2, plus or minus 1, and also 5/2 and 1/2. Each of these, when divided by 2, will end up giving me a duplicate, except for the 5 and the 1. So I don't have to worry about the others. again, this is a lot of choices. So what we'll want to do is we'll want to just plug in some numbers real fast and see what we end up getting out. This will help us eliminate some choices. So let's, for example, let's put this on a number line and let's see what we get if we do f of 0 first. 0 is not a choice, but I just want to see what it comes out to be. It will either be positive or negative, and that will help. So f of 0 ends up being 20. And then I'll check, say, f of 1. So that will be negative 217. Let's plug this into my calculator real fast. So that will be negative 2 times 1 cubed plus 19 times 1 squared minus 49 times 1 plus 20. And this comes out to be negative 12. Now, we'll pause for a moment. This is very, very helpful information because what this basically told me about my graph is that at 0, the graph has a y value of 20. And at 1, our graph has a y value of negative 12. And so that means that since this is a polynomial, it's a continuous function, somewhere in between, it has to cross at least once. Now, looking at my choices, there's only one of these choices that's between 0 and 1, which is 1/2. So let's divide 1/2 out. We're going to do it using synthetic division here. So I will put the 1/2 that I want here, and then I have negative 2, 19, negative 49, and 20. So again, we'll bring down the negative 2, multiply here gives me negative 1, and I get 18. Multiply here, 9, minus 40. Multiply here, minus 20, 0. Remember, we were expecting this 0 to come out because we knew that the only possible answer when I had between 0 and 1 was this root. And if it was going to be a rational root, 1/2 was the only choice. We could also have simply plugged in f of 1/2 into our calculator first and checked and made sure that it was equal to 0. But synthetic division doesn't actually take very long once you get very good at it. So it doesn't make too much of a difference whether you test with synthetic division or you test by plugging in. In any case, what we've got so far is we've now got this remaining polynomial, negative 2x squared plus 18x minus 40. Now we could continue again, checking additional rational roots, but why bother? At this stage, we're at a polynomial that's only a quadratic. We know how to factor this equal to 0. So just bringing this piece over here, I'll pull out a negative 2. That leaves me with x squared minus 9x plus 20. And I can factor this into x minus 4, x minus 5. Thus, my roots are 1/2, 4, and 5. And the polynomial factored into negative 2, x minus 1/2, x minus 4, x minus 5. Let's take a look at one more example here. Now, we could begin this one with synthetic division, but I want to remind us of an old technique that will work instead. If I say for a moment that y is equal to t squared, then notice what I get here. By making this substitution, I've changed this into a quadratic that I can factor out by hand. This becomes y minus 3, y plus 5. Now I get t squared minus 3, t squared plus 5, and I can factor further. This first piece fits the difference of squares, so that will be t minus root 3 and t plus root 3. This second piece will not factor. If I were to try quadratic formula, I would see that I would get a negative discriminant, meaning that there's no solution. And so this, for today, is the best we can do. But when we look at complex numbers, we will be able to do better. We'll be able to factor the piece on the right as well. For now, however, that's all we've got. So practice your synthetic division, practice your rational root theorem, and we'll see you guys next time.